Hello and welcome to our lesson on integration by parts. Basically, integration by parts is a technique that's going to be useful for integrals that not always but often involve products of algebraic and exponential or log functions. So again, we're looking for something typically that is the product of two functions. One of those functions would be an algebraic function like an x or an x squared or some polynomial, and then or radical, other things too we'll see, but then with that product you'll also see an exponential or a log function. So again, this isn't always the case, but it's often what we see when we're trying to use this process that we call integration by parts. Now, because it involves integrating a product, it just sort of makes sense that our integration by parts formula, the process that we use to integrate by parts, is based on a product rule for differentiation. So it's used to integrate a product, and the formula comes from the product rule for differentiation. So that you can connect this to the product rule for differentiation, which at this point we should be pretty comfortable with, let's start with that. If I said to differentiate with respect to the product of two functions, so let's call them f of x and g of x, then we know that this is going to end up being let's see, we shorthanded this before. We said f and g, and then we would say that the derivative for that product would be f prime g plus fg prime, but that's really shorthand notation. So it's going to be the derivative of the first, we'll say f of x, times the second function, so g of x, plus the first function multiplied by the derivative of the second function. Okay? So remember, when we're integrating, we're working in reverse. Instead of, let's take the derivative of our original function, and let's start with our original function, take the derivative, and then oh my gosh, my iPad is sliding all over. And then here's our derivative. When we're integrating, it's going in reverse. We're going to find the integral of the derivative, and that's going to take us back to our original function. So if I differentiate this and end up here, then when I integrate this, I end up here. So if I wrote that, what I just tried to explain, if I took the integral of this portion here, remember, take the integral of the derivative, I should get back to my original function. So I'm going to put f prime of x g of x plus f of x g prime of x here. And again, that integral differentiated with respect to x, that should take me back to the product of my two original functions. So f of x, g of x. Now I know as an integration rule that if I have the sum of two functions here, that I can split this up into two separate integrals. So this would be equivalent to the integral of f prime of x gx plus the integral of f of x g prime of x, and again still equal to f of x g of x. And then this is just an equation. If I want to manipulate this equation, I could, let's say, take this factor and move it to the other side by subtracting it, and that's what I'm going to do in my next step. So I'm going to leave this one here, the integral for f of x g prime of x. Oops, forgot my differential in that one. You hopefully were noticing that I forgot that differential. And now I gotta scoot all this over because I have OCD issues. Here we go. And okay, so back to, I'm going to take this term in my equation and subtract it to the other side. So let's not forget the differential again. I still have this f of x g of x here. And now I'm subtracting over the integral of f prime of x g of x. And again, that was differentiated with respect to x. And what I have here is a not so clean looking version of the formula that we're going to use to integrate by parts. So if we look at what this is saying now, if I'm taking the integral of a function multiplied by the derivative of a function, so that's the product of two functions, which is precisely what we're trying to integrate here, that is going to be equal to the product of the two original functions, minus the integral of the derivative of one function and the other function. So there's a lot going on in there, and I don't know that this formula looks like it's very simple, but to make it easier for us to digest all of the pieces that are here, notice in the actual formula we have u's and v's. So in place of f of x, we're going to call f of x u. In place of g of x, we'll call that v. So then we have two functions u and v, and we're going to say that those two functions u and v are differentiable functions of x. Then in this formula, if we're trying to integrate the product of u and the derivative of v, that would be like f and then g prime. If that's what we have in our product, a function and the derivative of a second function, then this is the formula we can use to simplify the integral. And so in this process, again, what we're going to start with is we're trying to take the integral of a product, and that product contains a function and the derivative of a separate function. And what this says, and this is just the product rule manipulated here, the product rule for differentiated manipulated, that it's going to be equal to the product of the two original functions, so u and v, or f and g as we looked at a second ago, and then we're going to subtract out an integral, and it's going to be v, that would be like our g, multiplied by du, that's the derivative of u, or f prime. So we have in this whole thing here 4 pieces. We have an original function u, we have an original function v, and we have the derivative of the first function and the derivative of the second function with some integrals, and these are all pieces that we're going to have looking back at this. So if I translate this into the simpler version here, again, f of x, g prime of x. So f of x is going to be replaced with u, so there would be a u here, there would be a u here, and then g of x is going to be replaced by v. So we're going to put a v here, going to put a v here, and then this would be f prime of x would be the derivative of u, and g prime of x is going to be the derivative of v. So I have the derivative of v here. And then all the components you can see exactly in the formula that we have up here. So the integration by parts formula, again, just a derivation of our product rule for differentiation. Again, if we took the derivative of a product, it takes us here, which means if I take the integral of this, it would take me back to the original function. So if I do that, separate this into two integrals, and then subtract this piece over, we end up with exactly our integration by parts formula. Okay, so hopefully that makes a little bit of sense, just to see where the formula comes from. Ultimately, though, we don't have to necessarily know where the formula comes from. It's just kind of nice to see that it's not dropping out of thin air. But ultimately, we have to be able to use the formula. Okay, so what we have to do is recognize when we have this situation, when we have the integral of a product, and in that product we can see two specific things happening, where we have a function and we have a derivative of a function. And then once we apply that, note that we need 4 pieces for all of this to happen. So we have a function, we have the derivative of a function. I need to figure out the 2 original functions, and I need the derivative for one of those functions, and I should be in good shape to apply this formula. Okay, so if we're going to use our integration by parts formula, first of all, it's not the simplest thing to do. It does require some work sometimes, and some of the work can honestly, it can get a little ugly. So we want to make sure that this is completely necessary before we even attempt to do it. Just because we see a product in an integral, it doesn't necessarily mean that, you know, the integration by parts is necessary. So if we can use substitution, and when I say substitution, I mean we see, you know, not x to a power but u to a power. We can apply that generalized power rule, or the natural log of not x but the natural log of u, as long as du is a factor of the integrand. If we can use substitution and apply that generalized integration rule, then that's going to be simpler than integration by parts. So for example here I see a product of 2 functions, and then here I see a product of 2 functions. Let me separate the colors here. So I have an algebraic function x, and then I have this exponential function here, and here I have an algebraic function 2x, and I have my exponential function here. Now, the first one is the one where I would have to use integration by parts. The second one, not. If you look at the second one, hopefully you can see the difference here. This would be like e to the u power. As long as du is a factor of the integrand, I can use substitution and just integrate using my e to the u power integration rule. And it is, because u is replaced by 2x, and then x squared, which means du is 2x. I don't want to go through the process of integration by parts for a situation where substitution is going to be possible. So I can substitute on this one. Oh my gosh, I don't know this thing. I think my app needs an update. We would just use substitution here. We would call this u, and then this would represent our du, and then we would just integrate using our e to the u power du rule, which means our integral would just be e to the u power plus c. Okay, now if we have a product where, again, this is just e to the x, so if I wanted to think about the derivative of x being a factor, well, the derivative of x would be 1, not x. In this product, I would be forced to use some other method. I could not use substitution because this is not du here. So this is one where I'm going to use integration by parts. Okay, so again, if we're going to try to use integration by parts, we have to recognize what we have. We need a product of two things, a function and a derivative of a function. So I need to recognize the product, and then I need to rewrite my integral so that I defined one piece of my integrand as our original function, and it's not an original function, as a function, let's just call it a function, and then dv, that's the derivative of some other function. So to apply the integration by parts formula, I like to start by rewriting. So you're going to rewrite the integral in the form u times dv. That means you want to split your integrand into two pieces. You're going to call one of the pieces of the integrand u, you're going to call the other one dv. And that seems easy enough, so just pick part of it, call it u, pick the other part of it, call it dv. But in order for this to work out nicely for us, we want to follow a couple of guidelines in making our choices for u and for dv. So in general, what we want is to let u be the portion of the integrand whose derivative is simpler than itself, and then dv would be the remaining portion. So for example, a good choice for u might be something like x squared, because if I took the derivative for x squared, I get 2x, which is absolutely a simpler function. Okay, so that's the goal. Pick for u a portion of the integrand whose derivative is simpler than itself. And also, when we're choosing dv, we need to make sure, so dv, that means it's a derivative. We need to be able to integrate it. So dv is generally going to be the more complicated portion of the integrand, but it's got to be something that we can integrate using a basic integration rule. And then, of course, u would be the other portion. So 2 guidelines. When we pick u, we want it to be a portion of the integrand whose derivative is simpler than itself. When we pick dv, we're looking for the more complicated part of the integrand, but also it needs to be something that we can integrate using a basic integration rule. Okay, so for example, let's say I was trying to look at the one we just saw a few minutes ago. Okay, if I wanted to integrate this product, I know I can't use substitution, so I'm decided, okay, I'm going to use integration by parts, which means looking at this integrand, I need to split it up so that some of it represents u and some of it represents dv. And there are a whole bunch of different ways we can do it. So I used parentheses so you can actually see the separation. Let's say I call x one part of it and then ex dx another part of it. So this would be u and then this would be dv. That's one possible way to split it up. Okay, so call x the u part of it, call ex dv, ex dx the dv part of it. And whatever part you choose for dv, note that dx would have to be in that portion because it is a derivative. Okay, or instead of separating that way, maybe I call e to the x u, and then the other portion x and dx could be the dv. Or maybe I lumped the whole thing together here and again just call 1, the invisible 1, our u, and call the whole product there dv. Or maybe I just lump together the product, call this u, and then maybe dx represents the dv. So you can see how there's got to be more, like we have to have guidelines in order to figure out, well, which way am I supposed to split this, because they're definitely not all equal. Alright, so in this particular case, what we want to do or which one of these options we're going to choose is, well, hopefully it will become clear. Let's look at this first option, okay? If this is the one I want to go with, remember, two guidelines. I want u to be the portion whose derivative is simpler than itself. So if I took the derivative of u, the derivative for x would just be 1. That's definitely simpler than x. And then dv needs to be the more complicated part of the integrand, and e to the x is more complicated than x, and it needs to be something I can integrate pretty easily, which I can. I can take the integral for e to the x pretty easily. The integral for e to the x dx would just be itself, e to the x, technically plus c. So this one meets both guidelines right off the bat, so this is looking like a good option. But let's go through the others so you can see what happens in those and why they end up being disqualified. So in this one, if I took the derivative of u, the derivative for e to the x would just be e to the x. That is not simpler than what I started with, so that would be a disqualification here. These two are exactly the same, not simpler. So for me that would be okay, I'm not going to use this method. Right? Not simpler than the e to the x we started with, okay? Or this one. So if I took the derivative of u, I get the derivative of a constant's got to be 0. Okay, so maybe 0 is simpler than 1, but I need to be able to take the integral for the dv portion, and this is the whole problem we started with in the beginning. I can't take this integral of this product unless I'm using integration by parts. So like I'm stuck here. So this definition for u and v not going to be good. This we can't integrate using a basic integration rule. Using a basic rule. Okay, or we go here. This one, if I go to take the derivative of u, remember I want the derivative of u to be something simpler, that's going to require the product rule, and the product rule, because it's x times e to the x, is definitely not going to make anything simpler than x and e to the x. It's going to in fact give me two products, so that's not simpler. Again, that would disqualify this. Not simpler. So we would have to use the product rule, and the result is not simpler than u. Okay, so just running through the different options here, the only one that meets both of the guidelines is that first one. So we would choose the first option because, let's see, dv, e to the x is the most complicated portion of the integrand. It fits the basic integration rule, and the derivative of x is just 1, which is simpler than the x that we started with. Okay, so once we've decided based on the guidelines what we should define as u and what we should define as dv, then the process is really just following a formula, although you can see in the formula there's a lot going on there. So after we apply the formula, we're still going to have to integrate. So let's look at it here. Let's actually try to complete the process. This is the same example we were just looking at. We said we're going to let x represent u, and then we're going to let e to the x dx represent dv. Okay, now back to my formula, which has 4 things. Remember, we're starting with this. That means we're starting with u and dv, and then in the formula we need u times v and v times du. So I need my u and you can see that I need v, right? I can see that I need du and I need dv. So I need u and v and du and dv, all 4 of those components. So back to our problem here. I just defined u, so that's going to be x. I just defined dv, I said that's going to be e to the x dx. I need to figure out du, and I need to figure out v, so that I have all 4 components that are in the formula. That's u and v and du and dv. So once we define u and dv, we need to do 2 things to find the other 2 components. Well, to get du, obviously, we're going to differentiate. So let's take the derivative. All right, if I have a function, I need to find the derivative of that function. I find a derivative. And then to go from here to here, that's backwards. So in this one, I have a derivative. I need to find the original function, which means I need to integrate or find the integral. Okay, so we define u and dv, and then we take the derivative of u to find du. We take the integral of dv to find v. Once we have all four pieces, from there, it's a formula. Okay, so the derivative for u, the derivative of x is just 1. Remember, that's differentiated with respect to x. We have to make sure to put that differential in there. And then I also need to find the integral for e to the x to figure out what my original function is. Well, the integral for e to the x, that's just e to the x. So this will be an e to the x here. Now, I know we differentiate and put a plus c typically. We can avoid that here, and I should have mentioned that. Let me back up to the other page here. I should have mentioned the plus c. What happens is we're going to end up with a plus c here when we take an integral, and we're going to end up with a plus c here when we take an integral, but because there's a minus, that's going to end up canceling out from both sides of the equation, and so we don't really have to worry about the plus c's until the very end of the process. Okay, so back to this one, we'll just let v be e to the x, not worry about that constant of integration until the very end of this process. Okay, so now I'm going to go over here and apply the formula. So this is going to be equal to remember our formula here. We have u times dv. We've already established what u was, what dv was. Now this is what it's going to be equal to. So it's u times v minus the integral of v times du. So u times v, that's these two pieces. So that's going to be x times e to the x minus the integral of is going to be v times du. So v, which is e to the x, times du, which is just 1 dx. And now we still have an integral in our problem, so even though we're using a formula to try to integrate, in the formula we still have to find an integral. But look at the integral we're left to find now, right? The integral that we're finding now is a very simple integral. So now we can continue here. I'm going to leave the product outside alone. X times e to the x minus the integral for e to the x is just e to the x plus our constant of integration. And we're done. We did it. Okay, and then remember, if you wanted to check your work, if you weren't sure, then you take the derivative of this, and it should take you back to this. This is the original function. You could take the derivative of that and get back to the integrand that's here. Okay, so let's try it again with this next example. So we're going to make sure substitution isn't a thing, but we're not going to be able to use substitution here. This is a product of two functions. We have an algebraic function, x squared. We have a log function here, and I don't know how to integrate using a basic rule, the natural log of x. So I'm going to do this in parts. Call one part u, call one part dv. Which part needs to be which? So let's say we wanted to just do exactly how we did the last one. Let's just call this first part u, and let's call this next part dv. Once you assign it, make sure the guidelines apply. So the derivative for u needs to be simpler. Well, the derivative for u would be 2x. That's definitely simpler. dv needs to be the more complicated portion. Sure, it is. But it also needs to be something that we can apply an integration rule to, a basic integration rule. Well, I don't have a basic integration rule for integrating the natural log of x, which means I cannot define this way, right? I cannot just integrate natural log of x. I know how to integrate 1 over x. That integral would be the natural log of x, dx, and this would be a plus c. But I don't have this. This is not a basic integration rule that we can apply. So now that that's done, let me try it a different way. Let me say that natural log of x is u, which means that the x squared and the dx would represent the dv. And see if this works, okay? So if I call u the natural log of x, then du is going to end up being 1 over x. Derivative for natural log of x is 1 over x. And then if I call dv the x squared dx, then v is the integral of x squared dx. Well, that's a pretty easy thing to integrate, right? I can apply a basic power rule to take that integral. And so this is going to be x to the third divided by 3. So we add 1 to the exponent and divide. So this would be x cubed divided by 3. And so here, let me just write that here as well. We're ready to apply our formula. So this is going to be equal to u times v. So we're multiplying u times v, and the order we multiply doesn't matter, so it's going to make more sense to have v as a coefficient of, or x cubed over 3 as a coefficient of natural log of x. So u times v, I'm actually going to do v times u. So x to the third divided by 3, and I like the coefficient option. So 1/3 x cubed multiplied by the natural log of x. There's my u times v. And that's going to be the front part of that. We're going to subtract from that v, remember our formula, v times du. So v, which is, again, our x cubed over 3 multiplied by du, which is 1 over x, and I did it again. This needs a differential. Otherwise, we have nothing here. So we need a differential of x. I have a bad habit of forgetting the differential, so don't let me slip on that, okay? All right, so that's v, and that's our du. Now, I'm going to clean this up. 1/3 x cubed natural log of x, that part looks fine. Minus, before I integrate this, we can definitely simplify here. We can cross-reduce a factor of x. Right, if 1 here, this is going to leave me an x squared here. So I'm going to end up with x squared over 3 in that integrand. X squared over 3, or if you wanted to make that 1/3 x squared, either way. I kind of go back and forth, and you can see that here. Okay, now we're ready to actually finish this off, because now this is in a cleaned up form and we can take that integral. So we're going to have 1/3 x cubed times the natural log of x minus, this will be 1/3, that's the 1/3 that's out here. I'm going to use my power rule to integrate. So 1/3, and then it will be multiplied by x cubed divided by 3. So add 1 to the exponent, divided by the new exponent, and then of course my constant of integration. So final answer, let's clean this up all the way, 1/3 x cubed natural log of x minus, this becomes a 1/9 x cubed, and then a plus c. And we did it. Okay, and again, if you weren't sure if you had done it correctly, because again there's a lot going on here, take the derivative with respect to x of what we just got here, and it should take you back to the integrand that you have here. So we're saying this is the original function that you can integrate to end up with this integrand as your derivative. All right, let's try it again. And if you're feeling good about this and you want to pause and give it a shot, but clearly this one looks slightly different. So I'm supposed to be separating this into 2 pieces, and yeah, I don't know. Any thoughts? Thoughts from the crowd? Yeah, I wish there was a crowd. It's much easier in class to get people to think about what we're doing here. Alright, so let's take a look. I think if I wanted to, let's just think about this. Call this u, and then just call this piece dv. I mean, I can't think of any other natural way to split this up. If you wanted to try to call, well, this is the differential. You can't call that u. Yeah, I can't see any other way to split this up. If you want to visualize like a 1 in front of this, then that might be helpful, but I think this will work because I can take the derivative of u, I get 1 over x, which is simpler, and I can integrate 1 dx, so I think I'm going to be in good shape. Let's do it. Let's call u the natural log of x, then the derivative of u would just be 1 over x, right? And then we just said let's let dv be 1 dx. Right, just the dx, or there's technically an indivisible 1 there, but I think seeing the 1 is helpful, because when I go to integrate that, I can take the integral for 1 dx. It's just going to be 1x plus c technically, but We just need the x. And so there it is. And now let's use our formula. All right, so this is going to be equal to, let me just go a little further so I can spread this out. So it's going to be u times v. That's going to be x and natural log of x in that product. Then I'm going to subtract the integral of v times du. So that's going to be x multiplied by 1 over x dx. And again, I forgot my differential here. Just really slipping tonight. Okay, so there's that. And before I actually integrate, that can be simplified. So x natural log of x minus, this becomes the integral of x times 1 over x is just 1. So this is just 1 dx. And again, you can see the integral now that we're taking is super simple. So x natural log of x minus the integral for 1 is going to be x, and then we have our constant of integration, and we're in good shape. I feel like I did something wrong. Maybe I didn't? What did I do? Hold on. Oh, I think I'm good. I don't know. Sorry, for some reason it feels like I made a mistake here, but I'm just going to go with it because it looks right. Double checking. Okay, here's what you should do, right? Let me practice what I preach. If I'm not sure that I did this right, I would take the derivative with respect to x of x, natural log of x, minus x plus c, and it better take me back to this. So let's see if it does. Okay, if I'm going to take this derivative, then I'm going to have to use my product rule here, call this f, call this g. I'm going to need f prime g plus fg prime. So that would be f prime, the derivative for x would be 1, times g, which will be a natural log of x. And then I'm going to add I think I said and wrote different things. F prime g plus fg prime. There we go. So f prime, again 1, g is just natural log of x, f would be x, and then g prime, so the derivative for natural log of x would be 1 over x, and then our derivative for minus x would just be minus 1, and then the derivative of the constant goes away. So this is the natural log of x, this becomes a positive 1, and then a minus 1, positive 1, minus 1 cancel, leaving me natural log of x. Perfect. Perfect again because what I have here matches what I have here. Okay? So I don't know why, but for some reason I had felt like I made a mistake because I don't know, just felt wrong for a second there. But clearly, after verifying my work, I can see that I did not, in fact, make a mistake. And so this is what you should do too. Remember, take the derivative of your integral. This should take you back to the integrand. This is the original function. This is the derivative. So checking your work, good option. Alright, let's try again the next one here. Before doing anything on this one, I would probably rewrite this. And I try when I have a fraction to rewrite if I can. It's not always conducive, but in this case, I can move e to the top of the fraction by making its exponent negative, so make that x times e to the negative x dx instead of a quotient, because I know how to handle the product now using my integration by parts. And so I'm going to call, this is very similar now to, we did one like this, right? X and e to the x is just a negative x now. So again, I'm going to call this piece of it u. I'm going to call this dv because e to the x is more complicated, but I can integrate, and the derivative for x is 1, and that's much simpler. So u is going to be x, which means the derivative for u is just going to be 1 dx. Look at me, not forgetting my differential. And then we said dv is going to be e to the negative x dx. And so now I need to figure out what v is. So to do that, remember I'm taking the integral for e to the negative x dx. Now this is not e to the x here, it's e to the negative x. So remember, when this changes to something other than x, we're using substitution, which means du needs to be here. So if u is a negative x, the derivative for negative x is negative 1. That means I need a negative or a negative 1 out in front here. So if I'm going to interject that, then I have to put a negative out here to undo it, so that I'm not changing my actual integral. Once that's there, then we can go ahead and integrate. The integral for e to the u is just e to the u. So this will now be multiplied by a negative. So a negative e to the u power, and then the plus c, which we don't need to worry about. So this will be a negative e to the negative x. All right, now I have all my pieces. And so now we're going to say this is equal to u times v. So multiplying u times v, just to put this in a nice clean order, I'm going to have a negative and an x and an e to the negative x. And then I'm going to subtract the integral of v times du. And du is just 1 dx, so that's nice. So a negative e to the negative x times 1 du, which is 1 dx. And now taking this integral is pretty simple. I just, in fact, did that a second ago. So this becomes negative x e to the negative x minus the integral for negative e to the negative x. Remember, this is u, and because this is not just e to the x, if this is u, as long as this is du, we're good, and it is. So the integral for e to the u is e to the u. This will be e to the negative x, and then our constant of integration. And this would be an okay way to leave the answer, although we tend to not like to leave negative exponents. So if I was going to clean this up, move the e to the bottom here, move the e to the bottom here, and then plus c. Although either one of those answers would be fine, this would be the version that I would prefer, and probably most would prefer. All right, last one, where we're finally going to look at something that's a little bit different. Again, I kind of mentioned that most of the time we're dealing with the product of an algebraic function and something that's exponential or logarithmic, but not always. So here's another example where we don't have an exponential or log function, but we can still use integration by parts. Now, similar to number 4, where I'm going to rewrite this to start, I don't want the quotient, I want a product to try to use my integration by parts. So I'm going to make this x times. This is 2 plus 3x to the positive 1/2 in the bottom of the fraction. So I'm going to make it 2 plus 3x to the negative 1/2 in the top of the fraction. And that way I have, again, the product of two functions. Now, this could be just a power rule, right, if this was u and this was du, but the derivative for u would be 3, not x. And so, integration by parts. Which one of these is the simpler part, or which one has a derivative who's simpler, and then which one can we integrate, which one looks more complicated but we can still integrate using a basic rule, I think is pretty clear in this one. So I'm going to call xu, and I'm going to call this the dv part. So if u is x, du is just 1 dx, and then we said dv is going to be this 2 plus 3x to the negative 1/2 power, because that is something I can integrate to find v. So when I go to integrate 2 plus 3x to the negative 1/2 power, remember this is something to a power, so I need du to be out here. That's not x to the power of negative 1/2, it's 2 plus 3x. So as long as du is a factor of the integrand, I'm good. Well, the derivative of 2 plus 3x is 3, so I need a 3 out here in order for my general power rule to work, which means I'm going to have to put a 1/3 out here. And now I can use my power rule. So this will be 1/3 times 2 plus 3x to the, add 1 to the exponent, so negative 1 over 2 plus 1 would be plus 2 over 2, so positive 1/2. And then we would have to divide by that same positive 1/2. And so this becomes 1/3 divided by 1/2 would be multiplied by 2. So this becomes 2/3 times 2 plus 3x to the 1/2 power. And that's my v. 2/3 times 2 plus 3x to the 1/2 power. Okay, so all that pre-work now just to finally apply the formula. So now we can apply our formula. This is going to be u times v. So when I multiply u times v, again, just to make this clean, I'm going to put the x right in between here, just so I don't have to write parentheses and, do a million steps more than I already am doing. So 2/3 times x, and then my 2 plus 3x to the 1/2 power. From that, I'm going to subtract the integral of v times du. Well, du is just 1 dx, so it's v, which is 2/3, and I left some space there on purpose, plus 3x to the 1/2 power multiplied by 1 dx, so just a dx here. Okay, so now my last piece is just to actually find this integral, but again, we're in a situation here where I have not x to a power, I have u to a power, so this needs to be du. And the derivative of u we said was going to be 3, so I need a 3 out here. So I need to multiply by 3/2, and then multiply. If I multiply by 3/2, that would undo the 2/3, and then multiply by 3 because I need a 3 out there. That means I need to multiply by 9/2 here. That gives me 18/6, which is 3. That's precisely what I need. And so if I put a 9/2 there, I need to put a 2/9 out here. Okay, so hopefully that how I worked through that made sense to you. So this is going to be equal to 2/3 x, 2 plus 3x to the 1/2 minus 2/9, and now I can use my general power rule because I have u and du. So I'm going to have 2 plus 3x. I got to add 1 to my exponent, so that becomes 3/2. Divide by the new exponent, which is 3/2. Add my constant of integration. And then just one more step because we want to clean up this complex fraction nonsense. So almost there. 2/3 x, 2 plus 3x to the 1/2 coming down, minus. If I divide by 3/2, that's the same as multiplying by 2/3. So if I have 2/9 and I multiply by 2/3, that becomes 4/27. So this will be 4/27, and then 2 plus 3x to the 3/2 power, and then plus c. And so this would be a perfectly acceptable answer. The only other way I might consider putting this answer is in radical form, since our problem started with radicals. So you could also say 2/3 x times the square root of 2 plus 3x here, and then 4/27 times the square root of 2 plus 3x cubed would be here, and then a plus c. But for the purposes of your homework, obviously the radicals are going to be not the nicest to even try to type in. So if you're doing this in Canvas, then this will be the option that you're going to go with. Maybe I'll even have you submit a picture of your work instead of having you type that in, because it's a little bit ridiculous. But the radical form or the rational exponential form, both would be totally fine. Okay, it's kind of similar to up here, both of these answers would be totally fine. It's just preferred to not have the negative exponents, so make the fractions here, but either one would technically be correct. Okay, so I'm hoping I'm giving you enough here to try to work through the problems that I've assigned to you in your homework, but as always, if you have questions, then please reach out. Until next time, take care.